from a theoretical perspective, understanding the resolution of a telescope is really just about understanding diffraction and what happens when light goes through some aperture. When we do that, the resulting product is a diffraction pattern like this. Essentially, you have some peak intensity at the center, but even if your light is infinitely thin, the ray of light, when it goes through, it will actually be blurred. So it means that when you hit a detector or your eye, you'll actually spread some amount, which will actually set the resolution, as we'll see. There will also be sort of second, third, and fourth order. They will start to become fainter and fainter, but they are important because they will be interfering if, for example, you have another source nearby where the images will start to be blurred. Now, this is called an Airy pattern, and perhaps looking at it in 1D makes more sense. So that's what I'm trying to do here in drawing the axis. Remember, my artistic skills are not the best. But if we actually take this image and essentially study the intensity as a function of position, so essentially cutting it through this direction, if we do that, what we'll be looking at is the intensity, essentially the amount of flux, as a function of some angular measurement or some coordinate that runs along this direction. If you do that, we can actually realize that we'll see some of these ripples coming up and then going to 0, then back again, then 0, and then this part that will correspond to the peak intensity, which should be around 1 at the center if we normalize it. The important thing to realize is that the first time that this peak drops to essentially 0 will be given by something like 1.22 lambda over d. And this essentially sets the resolution of a telescope, at least a theoretical resolution. We can see this more clearly on the figure here on the right that is better than my handwriting. And this establishes essentially the angular resolution, delta theta, in radians. This is incredibly important. It is in radians because lambda and d will be on the same units. This was a quantity that's unitless, and in this case, we will be measuring it, the angle, in radians. And this, which we'll use in physics 263, is also called the Rayleigh criterion. An important question to ask, though, is why is this the ultimate resolution limit? What sets this as the value that we should use for the minimum distance between two sources in terms of angles for us to see them as two sources? Now, this can be very easily seen if instead of just looking at an Airy pattern of a single source, we do it for two and we take sources to be closer and closer together. Essentially, this quantity of 1.22 lambda over d corresponds to this case, the point at which you can still see the sources as two, but if you make them closer, they will blur as one. And this is also illustrated here on the side, is that this specific distance at 1.22 lambda over d, and I mean angular distance, corresponds to the point at which when you image these two sources, they are barely resolved, as you can see here. If you make them even closer, it will just look like a blurred, larger source, and you will no longer be able to identify them cleanly as two sources. So remember, if you want to calculate the theoretical resolution limit of a telescope, that will depend on the wavelength that you're observing and the diameter of a telescope. And it's 1.22 lambda over d, and never forget that delta lambda will come out as radians. If you want to use arc seconds, you'll have to convert it, obviously. A nice example of why resolution matters, in this case in the optical, can be seen even in our own solar system. In these two pictures that have actually been combined, you can really see the difference between imaging the same place, this case is the surface of Venus, when you look with something that is quite poor in resolution. The resolution in this case is something like 1 kilometer. It means anything that's closer than 1 kilometer, or that is not at least 1 kilometer apart, you will see it as a single pixel. You won't be able to distinguish it, versus imaging with a much higher resolution instrument that allows you to distinguish things down to something like 75 meters. And you can definitely see the huge difference in resolution and detail. The reason why we want high resolution is because that will allow us to actually unveil the details that otherwise we would miss completely. And this is even more important when you go out way beyond the solar system and we start studying, for example, solar systems information, like you see here. This is a protoplanetary disk observed with ALMA that achieves an amazing resolution of 0.04 arcsecond at a really long wavelength. Now, if you're plugging in the numbers already and trying to calculate the diameter of this telescope that at 800 microns can actually get a resolution of 0.04 arcsecond, you're definitely in the right track, because that's what we're going to do now. In order to calculate the aperture of a telescope, given some resolution as you see here and some lambda, we could just use a Rayleigh criterion, essentially 1.22 lambda over d. And it's good to reinforce the fact that if you want to use that formula with wavelength and diameter in the same units, as you should, then you need to either convert this to radians, or you can convert the formula to arcseconds, like I'm doing right now. If you do it, you'll get a formula that is essentially 250,000 times lambda over d, where lambda and d in this case could just be in meters. If we were to plug in the values, that number of 251,643, and actually multiply by 800 microns divided by some diameter, and then solving for the diameter, we'll realize that the telescope required to get this resolution has a diameter of 5 kilometers, which is really impressive. And you think, wow, I want to work with ALMA. And then you Google ALMA and you realize that there's no such telescope with a 5 kilometer diameter. What this actually implies, and I also have the calculations here in a cleaner way and not handwritten with the power of my mind, that's always challenging. If you do these calculations, you get a value of 5 kilometers. But as I was trying to tell you, there is no such thing as a telescope with 5 kilometers. What we actually do have is a neat technique where we can combine different telescopes, and where instead of using this d, we'll be using the distance, the largest distance between telescopes or antennas. And at the end of this playlist, we will discuss a little bit about this technique, which is called interferometry.